Testing my mic. Now let's switch back to my coding overlay here. And there we go, we are officially live now. Welcome back, and this is day 10 of me learning Pytorch. I'm really excited for what we're about to learn today, and yeah, let's continue with our journey. So excited, we're on day 10 now. Let's begin.
Comprehensive course will teach you the foundation.
So yesterday we were able to make predictions on our fashion MNIST model, and yep, we reached the, I think it was the 19-hour mark, wasn't it?
Mega taskers are not quick.
This comprehensive course will teach you the foundations
Why
of
is
machine
that
learning
again,
and
though?
deep learning using Pytorch.
Visualize now. Set the scene. In the next video, we're going to plot these and compare them. So we're going to write some code to create a matplotlib plotting function that's going to plot 9 different samples along with their original labels and their predicted label.
We already covered that.
Welcome
part.
back. In the last video, we wrote a bunch of code to import some extra libraries that we need for plotting a confusion matrix.
Oh,
This is really helpful, by the way. Google Colab comes with a lot of pre-built installed stuff, but definitely later on down the track, you're going to need to have some experience installing stuff. If it
Did not reach this part for sure.
confusion matrix. So recall. Let's now continue following the data we have, but along it because of a minute and create in on humor square going human in going in depth to do range and play next by the plot font text cred club plot title. See what we
I
did.
need some kind of bookmark extension if they have them on.
Oh, I'm going.
You know, what does Chrome call its extension store again? Chrome Web Store, right? Yeah. I need to look into it.
I'm going to do one more thing. I want to turn off the axes. Kind of plot this visual it sample different sample here. Correct. Press next video. So our model seems to be two again. Okay, well, I can kind of see where the model might have stuffed up there. It's a little bit long for a shirt for me, but maybe labels in your D is our model's results better or worse than they actually are. And that's what visualizing helps you do, is figure out, you know what, our model, try look at some, and we'll move on to the next video. We're going to go on to another way. Oh, see, this is another example. Some labels here could be confusing. And speaking of confusing, well, that's going to be a spoiler for the next video.
Alright, this is the part where we should continue our video at. So,
But
yeah, let's go.
you see how the prediction is a t-shirt top, but the truth is a shirt? To me, that label is kind of overlapping. Like, I don't know, what's the difference between a t-shirt and a shirt? So that's something that you'll find as you train models, is maybe your model's going to tell you about your data as well. And so we hinted that this is going to be confused. The model is confused between t-shirt top and shirt. How about we plot a confusion matrix in the next video? I'll see you there. We're up to a very exciting point in evaluating our machine learning model, and that is visualizing. And we saw that in the previous video. Our model kind of gets a little bit confused, and in fact, I would personally get confused at the difference between t-shirt / top and a shirt. So these kind of insights into our model predictions can also give us insights into maybe some of our labels could be improved. And another way to check that is to make a confusion matrix. So let's do that, making a confusion matrix for further prediction evaluation. Now, a confusion matrix is another one of my favorite ways of evaluating a classification model, because that's what we're doing. We're doing multi-class classification. And if you recall, if we go back to section 2 of the LearnPytorch.io book, and then if we scroll down, we have a section here, more classification evaluation metrics. So accuracy is probably the gold standard of classification evaluation. There's precision, there's recall, there's F1 score, and there's a confusion matrix here. So how about we try to build one of those? I want to get this and copy. There's precision, there's recall, there's F1.
Description say? Compares the predicted value with the true values in a tabular way. Okay. If 100% correct, all values in the matrix will be top left to bottom right. Like it will be in a diagonal line, huh? Okay, I'll have to see that to me for it to make more sense. Yeah.
One score, and there's a confusion matrix here. So how about we try to build one of those? I want to get this and copy this. So, and write down a confusion matrix is a fantastic way of evaluating your classification models visually. Beautiful. So we're going to break this down. First of all, we need to deploy a confusion matrix. We need to make predictions with our trained model on the test data set. Number two, we're going to make a confusion matrix. And to do so, we're going to leverage torch metrics. Tricks, I have to figure out how to spell metrics then. Confusion matrix. So recall that torch metrics is...
I'll have to run all of this again, don't I? Let's just get that started.
This before is a great package, Torch metrics, for a whole bunch of evaluation metrics of machine learning models in Pytorch flavor. So if we find we've got classification metrics, we've got audio image detection, look how this is beautiful. A bunch of different evaluation metrics. And if we go down over here, we've got confusion metrics. So I only touched on 5 here, or 6. But if you look at Torch metrics, they've got, how many is that? About 25 different classification metrics. So if you want some extra curriculum, you can read through these. But let's go to confusion matrix. And if we look at some code here, we've got Torch metrics, confusion matrix, we need to pass in a number of classes. We can normalize if we want. And do you notice how this is quite similar to the Pytorch documentation? Well, that's the beautiful thing about Torch metrics, is that it's created with Pytorch in mind. So let's try out, if you wanted to try it out on some tester code, you could do it here, but since we've already got some of our own code, let's just bring in this. And then number 3 is to plot it. We've got another helper package here. Plot the confusion matrix using ML extend. So this is another one of my favorite helper libraries for machine learning things. It's got a lot of functionality that you can code up yourself, but you often find yourself coding it for you too many times, such as plotting a confusion matrix. So if we look up ML extend, plot confusion matrix. This is a wonderful library. I believe it was created by Sebastian Rashka, who's a machine learning researcher and also author of a great book. There he is. Yeah, this is a side note, Machine Learning with Pytorch and Scikit-learn. I just got this book. It just got released in the start of 2022, and it's a great book. So that's a little side note for learning more about machine learning with Pytorch and Scikit-learn. So shout out to Sebastian Rashka. Thank you for this package as well. This is going to just help us plot a confusion matrix like this. So we'll have our predicted labels on the bottom and our true labels on the side here.
What happened here? Name device is not defined. That's because device is defined here. How do we run from this? Okay, run after this is what we should do then. Run after.
But we can just copy this code in here. Link, sorry, and then confusion matrix, we can copy that in here. The thing is that Torch metrics doesn't come with Google Colab. So if you're using Google Colab, I think ML extend does, but we need a certain version of ML extend that Google Colab doesn't yet have, yeah. So we actually need version 0.19.0. But we're going to import those in a second. Let's first make some predictions across our entire test dataset. So previously, we made some predictions only on 9 random samples. So random sample, we selected 9. You could, of course, change this number to make it all more, but this is only on 9 samples. Let's write some code to make predictions across our entire test dataset. So import tqdm.auto for progress bar tracking. tqdm auto. We don't need to re-import it, I believe we've already got it above, but I'm just going to do it anyway for completeness. And so we're going to make, this is step 1. Above, make predictions.
Oops, that failed. How did that fail? Expected all tensors to be on the same device. I don't want to debug that right now. I guess oh, we need the second. We only need this, so let's just run that. Let's just train our model 2 real quick. Set up the loss function. Have we defined model 2? No, we have not defined model 2. And now set up loss function and optimizer. And now let's train it. Train step is not defined. Let's go up. Yep. And now if we go ahead and train it, should work now. What's the runtime? Yeah, it's using a uClaw, right? That should take less time, hopefully. 13 second, yeah, around 13.5 seconds per iteration. Actually, no, it's not 13.5, is it? because this needs to be needs to reach 99, like there are 100 digits here. Great. That should do it, hopefully. And
Make
yeah,
predictions
it
with
says uh there was a function though. Let's just define it.
trained model. Our trained model is model 2. So let's create an empty predictions list so we can add our predictions to that. We're going to set our model into evaluation mode, and we're going to set with Torch inference mode as our context manager. And then inside that, let's just build the same sort of code that we use for our testing loop, except this time we're going to append all of our predictions to a list. So we're going to iterate through the test data loader, and we can give our TQDM description. We're going to say making predictions, ... You'll see what that looks like in a minute. And here we're going to send the data and targets to target device. So xy equals x to device and y to device. Wonderful. And we're going to do the forward pass. So I'm going to create y logit. Remember, the raw outputs of a model with a linear layer at the end are referred to as logits. And we don't need to calculate the loss, but we want to turn predictions from logits to prediction probabilities to prediction labels. So we'll set here ypred equals torch.softmax. You can actually skip the torch softmax step if you wanted to and just take the argmax of the logits, but we will just go from prediction probabilities to pred labels for completeness. So squeeze, and we're going to do it across the first dimension, or the 0th dimension, and then we'll take the argmax of that across the first dimension as well. And a little tidbit, if you take different dimensions here, you'll probably get different values, so just check the inputs and outputs of your code to make sure you're using the right dimension here. And so let's go put predictions on CPU for evaluation, because if we're going to plot anything, that plot lib will want them on the CPU. So we're going to append our predictions to ypreds, ypred.cpu. Beautiful. And because we're going to have a list of different predictions, we can use concatenate, list of predictions, into a tensor. So let's just print out ypreds so I can show you what it looks like. And then if we go
So we get our logits, which we turn into our predictions by using softmax. Just for the sake of it, I want to see what the logits and softmax look like. As a refresher. So what we'll do is hmm, let's look at the y logit first. Let's also put manual C. Data loader object is not subscriptable. How do I just want the first 10 elements. Get first 10 elements from data loader object item. I know, but let's just copy this. Ugh. We can just do that test of list of we can just convert that to a list and then take the first one element and this should work. Okay, this is what the logits look like. This has 10. What's the shape. Thirty to 10 because it's taking. Okay, these are the predictions for 32 images, right? Because we not that's what data loader does, right? It makes batches of images. Now this doesn't all add up to one, but some of the softmax function makes them add up to one. What exactly does the softmax do behind the scenes? Like, what is the mathematical operation behind it? Yeah, we need to look at the math side of it, but the graph explains a lot. It squeezes each input between 0 and 1, and somehow via math, all of them adds up to 1, and we get probabilities that we can use. Great. Anyhow, you know what? Let's take a look at the graph again. Yep. So if it's a negative value, oh, okay, I see. The more negative the value is, the more, yeah, the more close the probabilities to 0, and the more positive what is it logit is, the more closer it is to 100% or 1. All right, and it uses where's the formula? Yep, softmax formula. It uses this formula apparently to do this magic. Not magic, it's math. Alright. So that's what logic does, and to convert it to predictions, we apply softmax, and yeah, we remove the actually well, let's take a look at the this. I also want to see the I mean the why logit has is this gonna add a what is space to again, and it removes or adds a bracket? What does space do in Python? Yeah, it removes the outermost bracket if any, like if it's of dimension 1. All right, okay, and then the softmax is applied to each prediction, so all of these should add up to 1. I'm just gonna do rough math in my head. 1 and -9, -8, -1. Hmm. Do all of them add up to 1, or can I, by chance, I need a new, what's, that doesn't add up to 1? Wait, what? Was I lied to? I thought they had to add up to 1, right? Softmax add up to 1? Yep, okay, gotcha. Then why isn't it doing that? that turns a vector of k real values into a vector of k real values at sum to 1. Oh, this is the logic part, isn't it? I was looking at, no, wait, I copied the correct one. I'm not applying the softmax here, that's the reason. Okay, let's apply the softmax function and then test it. This is an invalid combination of arguments. Got tensor but expected one off. I made some mistake here apparently. Oh, this is why we take the dimension 0. Wait, what is dim 0 and Pytorch? Is it the like this one or like the inner one? No, I mean get 2 dimensions because it has 2 brackets. But I want to see the so the dimension or dimensions to reduce. We're gonna do some experimentation right now. Name it X. All right, and if we do torch dot mean, mean could not infer output data type. Input data type must either be or should it be plotting point. Oh, okay. Torch dot plot. What if I add another set of brackets? I guess it will squeeze it. What if I do this then? Alright, I'm a bit experimenting right now, I guess. Okay, let's do this and see what happens. So we're trying to find out, or I know you know, the tutorial has covered this in the beginning, but I wanna see what the dimensions are like. Is this the zero dimension or is this the zero dimension? See? I'm gonna do this. And alright, okay. Not what I expected. Oh yeah, there we go. Someone has already asked this question. Yeah, the dim parameter dictates across which dimension the softmax operation is done. To transform your input into probability distribution, the sum of all elements will be 1. It will show me an example. I wrote a small example which shows difference between using dimension 0 and 1 for 2D input tensor. Alright, okay. These are the inputs. If we apply dimension 0, these add up to 1. I mean, does this array add up to 1? Let's see. 18231431 does not add up to 1. Does this add up to 1 then? 1927153. Yeah, this I think would add up to 1. Yeah. Okay. So as you can see for this software, sum of each column is equal to 1. With dimension 0, yeah, each column is 1, like this. So 1 8, each column is 1. Oh, sorry, this is the this is the one. Yeah. Oops. Yeah. 1832, and you have 2621. Yeah, that adds up to 1. For dimension 1, it is the sum of the rows that is equal to 1. Usually you want to perform a softmax operation across the patch dimension. Gotcha. Okay. So the 0 dimension, it just applies softmax across like in a straight line, where I mean, yeah, straight line. But if the dimension is 1, then it applies it across a row. Alright, okay. And here, what are we given here? We have given dimension 0. Dimension 0. Let's add this. No, not the dimension. No, no, not the dimension. I want to see what the biology.squeeze looks like. So if this applies softmax, adding the 32 elements, if this were spread like white, would add up to 1. Why would you want to do that? Um, let's print with the softmax applied on dimension 1. No, the second one is just the shape, so we leave it as it is. Oh, okay. Maybe dimension 0 is it's not okay. Softmax received an invalid combination of arguments. Got tensor but expected one of oh, it's because I have not specified this here. What is okay, softmax that alright, and let's see here. 2.7, 1.85, 3. That isn't. Oh, they have different exponents here, so it doesn't add up to 1 because you need to sum these rather than that. That this uh indexing or slicing. So I want to slice it like in a straight line. NumPy slicing cheat sheet. See, I want slicing. Select items row 0 and 1. Okay, 0 to 1, column 1. Oh, so we just need to do, this is 2 and 8, okay? 2 and 8. 2 and 8, 2 and 8. See, this should work. 2 and 8, yeah, there we go. That is 1. Okay, and now my question is, why would you wanna do this though? What's the point of doing it via like a straight line? Shouldn't you be doing it the other way? Like you're trying to classify predictions between each probability inside inside for each class, right? Not for each image. All right. Okay, let's remove this. Do this. Let's look at this again.
Go widespread tensor. This is going to turn our list of predictions into a single tensor, and then we'll go widespread tensor, and we'll view the first 10. Let's see if this works. So making predictions. Oh, would you look at
That worked, but then let's go to data loader again. So this represents one entire image. So you would wanna apply softmax like this rather than this. Maybe I should look at it from a different angle. Softmax logit piece. Turning prediction from logits into prediction probability. What happens if I take the first dimension? That's one, alright. Which them to take in softmax? Yeah, exactly. You want to perform it across. Really, I agree, but then oh, it is this. Oh wait. Okay. Okay. Cool. Uh, you'll want to perform the softmax operation on the logist dimension. For example, if batch size is equal to 1, you can perform it on dimension equal 0. There's only one value. Alright. Okay, okay. So, oh, we have finally achieved the follower goal. Yeah, there we go. Thank you, long live Kyo. Pretty sure that's not a real name. Man, yeah. Anyway, we achieved our follower goal, so yeah, kudos to us. Alright, we'll set a new goal later. For the time, we'll just go back to the problem at hand here. So, where was I? Yeah. That makes sense. If the batch size is 1, since there's only one image, you can use dimension 0, dimension 1. In chapter 3, use a dimension is equal to 0 and dimension is equal to 1 for softmax. but one had 32 as a batch, and want to perform the softmax operations on the logit dimension. I know, which means here we should be using one. Let's just
YPred
go to the
tensor
video.
and it's data loader, so there's 313 batches of 32. So if we comment out print YPreds, this line here, preds is going to turn these tensors.
No, it doesn't change it. You know what? For the sake of it, let's just put 0 and see. Mean if the predictions are wrong, then we'll spot it, right? So yeah, let's do that. Maybe someone likely, but let's check the comments. Them no, yeah, them them. No, all right, okay. All right,
Matches of
let's
32.
just go with this, and yeah, we take the arc max, of course.
So if we comment out print YPreds, this line here, torch.cat YPreds, is going to turn these tensors into a single tensor, or this list of tensors into a single tensor. Concatenate. Now if we have to turn these tensors into a single tensor, or this list of tensors into a single tensor. Concatenate. Now if we have a look, there we go, beautiful. And if we have a look at the whole thing, we're making predictions every single time here, but that's all right. They are pretty quick. There we go. One big long tensor. And then if we check length YPred tensor, there should be one prediction per test sample. 10,000. Beautiful. So now we need to install Torch Metrics, because Torch Metrics doesn't come with Google Colab at the time of recording. So let me just show you if we try to import Torch Metrics. It might in the future, so just keep that in mind. It might come with Google Colab because it's a pretty useful package. But let's now install, see if required packages are installed, and if not, install them. So we'll just install Torch Metrics. We'll finish off this video by trying to import. We'll set up a try and except loop. So Python is going to try import Torch Metrics and ML extend. I write it like this because you may already have Torch Metrics and ML extend if you're running this code on a local machine. But if you're running it in Google Colab, which I'm sure many of you are, we are going to try and import it anyway. And if it doesn't work, we're going to install it. So ML extend, I'm just going to check the version here because we need version for our plot confusion matrix function. This one, we need version 0.19.0 or higher. So I'm just going to write a little statement here. Assert int ML extend dot version. So if this condition in the try loop or try block is accepted, it will skip the next step. dot split, and I'm just going to check the first index string is greater than or equal to 19. Otherwise, I'm going to return an error saying ML extend version should be 0.19.0 or higher. And so let me just show you what this looks like. If we run this here. String and int. Did I not turn it into a string? Oh, excuse me. There we go.
Oh, all right.
And I don't need that bracket on the end. There we go. So that's what I'm saying. So this is just saying, hey, the version of ML extend that you have should be 0 or should be 19 or higher, because right now Google Colab by default has 14. This may change in the future. So let's finish off this except block. If the above condition fails, which
Incomplete input.
it should, because right now Google Colab. So this is just saying, hey, the version of ML extend that you have should be 0 or that bracket on the end. There we go. So that's what I'm saying. Excuse me. There we go. And I don't need that bracket on the end. There we go. So that's what I'm saying. So this is just saying, hey, the version of ML extend that you have should be 0 or should be 19 or higher, because
incomplete input. What does that mean? Incomplete input.
right now Google Colab by default has 14. This may change in the future. Let's finish off this except block. If the above condition fails, which it should, we are going to pip install. So we're going to install this into Google Colab. Torch metrics, we're going to do it quietly. And we're also going to pass the U tag for update ML extend. So import torch metrics, ML extend afterwards, after it's been installed and upgraded, and print. We're going to go ML extend version. We're going to go ML extend underscore version. And let's see what happens if we run this. So we should see, yeah, some installation happening here. This is going to install torch metrics. Oh, do we not have ML extend, the upgraded version? Let's have a look. We may need to restart our Google Colab instance. Ah, okay. Let's take this off. Quiet. Is this going to tell us to restart Google Colab? Well, let's restart our runtime. After you've run this cell, if you're using Google Colab, you may have to restart your runtime to reflect the fact that we have the updated version of ML extend. So I'm going to restart my runtime now. Otherwise, we won't be able to plot our confusion matrix. We need 0.19.0. And I'm going to run all of these cells. So I'm going to pause the video here, run all of the cells by clicking run all. Note, if you run into any errors, you will have to run those cells manually. And then I'm going to get back down to this cell and make sure that I have ML extend version 0.1.9. I'll see you in a few seconds. I'm back. And just a little heads up, if you restart your runtime and click run all, your Colab notebook will stop running cells if it runs into an error. So this is that error we found in a previous video where our data and model were on different devices. So to skip past that, we can just jump to the next cell and we can click run after. There we go. And it's going to run all of the cells after for us. It's going to retrain our models. Everything's going to get rerun, and then we're going to come right back down to where we were before, trying to install the updated version of ML extend. I'm going to write some more code while our code is running. Import ML extend, and then I'm going to just make sure that we've got the right version here. You may require a runtime restart, you may not. So just try to see after you've run this install of torch metrics and upgrade of ML extend. See if you can re-import ML extend, and if you have the version 0.19.0 or above, we should be able to run the code. Yeah, there we go. Wonderful. ML extend 0.19.0, and we've got ML extend version, assert, import. Beautiful. So we've got a lot of extra code here. In the next video, let's move forward with creating a confusion matrix. I just wanted to show you how to install and upgrade some packages in Google Colab if you don't have them. But now we've got predictions across our entire test data set. And we're going to be moving towards using confusion matrix function here to compare our predictions versus the target data of our test data set. So I'll see you in the next video. Let's plot a confusion matrix. Welcome back. In the last video, we wrote a bunch of code to import some extra libraries that we need for plotting a confusion matrix. This is really helpful, by the way. Google Colab comes with a lot of pre-built installed stuff, but definitely later on down the track, you're going to need to have some experience installing stuff, and this is just one way that you can do it. And we also made predictions across our entire test data set. So we've got 10,000 predictions in this tensor, and what we're going to do with the confusion matrix is confirm or compare these predictions to the target labels in our test data set. So we've done step number 1, and we prepared ourselves for step 2 and 3 by installing Torch metrics and installing ML Extend, or the later version of ML Extend. So now let's go through step 2, making a confusion matrix, and step 3, plotting that confusion matrix. This is going to look so good. I love how good confusion matrix is. Look. So because we've got Torch metrics now, we're going to import the confusion matrix class, and from ML Extend, we're going to go into the plotting module and import plot confusion matrix. Recall that the documentation for both of these are within Torch metrics here and within ML Extend here. Let's see what they look like. So number 2 is set up confusion matrix instance and compare predictions to targets. That's what evaluating a model is, right? Comparing our model's predictions to the target predictions. So I'm going to set up a confusion matrix under the variable conf map. Then I'm going to call the confusion matrix class from Torch metrics. And to set up an instance of it, I need to pass in the number of classes that we have. So because we have 10 classes, they are all contained within class names. Recall that class names is a list of all the different classes that we're working with. So I'm just going to pass in the number of classes as the length of our class names. And then I can use that conf mat instance, confusion matrix instance, to create a confusion matrix tensor by passing into conf mat, which is what I've just created up here. Conf mat. Just like we do with our loss function, I'm going to pass in preds equals our y pred tensor, which is just above y pred tensor that we calculated all of the predictions on the test data set. There we go. That's our preds. And our target is going to be equal to test data dot targets.
We're gonna pass our prediction tensor and our ground truth. What happened there? Yeah.
And this is our test data dataset that we've seen before. So if we go test data and press tab, we've got a bunch of different attributes. We can get the classes. And of course, we can get the targets, which is the labels. Pytorch calls labels targets. I usually refer to them as labels, but the target is the test data target. So we want to compare our model's predictions on the test data set to our test data targets. And so let's keep going forward. We're up to step number 3 now. So this is going to create our confusion matrix tensor. Oh, let's see what that looks like, actually. Conf mat tensor. Ooh, okay. So we've got a fair bit going on here, but let's turn this into a pretty version of this. So along the bottom is going to be our predicted labels, and along the side here is going to be our true labels, but this is where the power of
Conf mat missing one require positional argument task. Okay, maybe confusion matrix. What is his name again? Torch matrix. Let's see. And they say we need a thing called task. So what should have task? Missing one require positional argument task. Alright. But this doesn't say anything like that. Right, we'll use this. Maybe it's just the title or something, you know, man. Okay, and target with shape.
ML Extend comes in.
Something is definitely wrong with the way that we are doing things. Let's see. The predictions and targets should have the same shape. Prediction and target should have. Our prediction Something is wrong here. All right, okay.
Version of this. Pre now is the text. And of course, that we've seen before preds is just created up here. Conf is a list of what we need to pass in under the pre-ML extend here. Let's see what they look like. So number 2 is set up confusion target predictions. So I'm going to set up, I need to pass the different classes that we work matrix instance. Our loss function, I'm going to pass in pred. There we go. That's our preds.
The shape is the same. Shape is the same, alright? Oh, okay. Alright, okay.
And our target is going to be equal to test data dot targets. And this is our test data dataset that we've seen before. So if we go test data and press tab, we've got a bunch of different attributes. We can get the classes. And of course, we can get the targets, which is the labels. Pytorch calls labels targets. I usually refer to them as labels, but the target is the test data target. So we want to compare our model's predictions on the test data set to our test data targets. And so let's keep going forward. We're up to step number 3. Bottom is going to be our predicted labels, and along the side here is going to be our true labels, but this is where the power of ML extend comes in. We're going to plot our confusion matrix. So let's create a figure and an axis. We're going to call the function plot confusion matrix that we've just imported above, and we're going to pass in our conf_mat equals our conf_mat tensor. But because we're working with matplotlib, it'll want it as numpy. So I'm just going to write here, matplotlib likes working with numpy, and we're going to pass in the class name so that we get labels for each of our rows and columns. Class names, this is just a list of our text-based class names, and then I'm going to set the fig size to my favorite hand in poker, which is 10.7. Also happens to be a good dimension for Google Colab. Oh, look at that! Oh, that is something beautiful to see. Now, 10.7. Also happens to be a good dimension for Google Colab. Oh, look at that! Oh, that is something beautiful.
Alright, let's put that in there and hit run, and where turns objects has okay, so we need to do dot, we need to put this onto numpy, and there we go. Okay, we got it.
Beautiful to see. Now,
Yeah, ours is wrong. I can just, because from that definition that I read somewhere, it should be like a diagonal, right?
a confusion matrix, the ideal confusion matrix will have all of the diagonal rows.
Yeah, which means oh, this should be 0. Okay. Okay, something is going on here. Let's see. Did I train the model, or I trained the model, alright? Okay, alright. Hmm. Something is wrong probably at this part of the code. Okay, we need to open up the notebook, non-pytorch.io notebook. So, I know this doesn't change anything, but let's remove that. Um, then what? They use dimension as one here. Not bash dimension. So was okay, okay. We'll check until we check into it. But let's just see. Still ain't working. Function one. Alright, okay, what's happening here? How can we figure this out? Just to see if this is the type, I'm just gonna actually, you know what? Let's do it in a new code block. Okay, then this is troubleshooting on the fly here. Hmm. Let's see. This is the squeezed version. What about just like without the squeeze? It's the same. What? Hmm. Right. How do we resolve this? Using the test data here. With answer. And then we'll also print out the target. And we'll print out the index like this. And all right. Let's see whether there's anything. That says a lot. It is wrong for some reason. It's for us to figure out why. Our model is accurate. So something is wrong with the code that we wrote. You want print this for me, please? And let's just do a new code block here. This should, yeah, it adds up to one, all right. So that means that part of it is correct, and we're taking the arg max. This is softmax. We're taking the arg max across the first dimension itself, which is across this, which is also correct. I mean, at least it should be correct. Now you don't need to print that out, but yep, that's definitely wrong. So let's see what we can do here. Yep, let's see. For the sake of it, I'm just gonna change this to 0 and see what happens. Definitely not an 89% accuracy that we have there. Um, okay. Let's think here. We get the logics, we make the predictions. We are definitely using the test data loader. Hmm. Change that to the first dimension and hmm. Let's just go up a bit. Let's go up a bit. It's working great till here. Let's go to our make predictions function. So we do the forward pass here. Hmm. Make predictions. Let's go to that section. So this function works. Um, could it be because of this? We are using model 2 itself, right? Yeah, we are. Unlikely, but no harm in trying. Torch dot inference more for same sampling data. You can squeeze the sample, and what is data? Test sample. We're just taking a sample from that. Okay, this is I think this is our biggest troubleshooting. You know, I don't want to call it a session, but it is turning out to be a session. Yeah. It's turning out to be long. Anyhow, let's see. Hmm. I understand why he did squeeze there because it is just one single image. There are the 32 images. In that sense, we are passing data separately as separate image. That works. Wait, do we have? I thought we had two functions for some reason. And we take the arc max across the first dimension. Mhm. So, um, should we do here? You know what? I'm gonna take a break and maybe we'll figure this out when we come back. All right, I am back. So here's what we can do to where's my hair? Like every time I come back, my hair is messed up. Okay, so here's the idea. We're gonna run the collab notebook that Daniel had already written, and then look at the shape of what he got and compare it against what we have. That way, we'll be able to debug what's going on here. So let's do that. Well, I thought I could do that, but apparently not. Maybe oh yeah, there's an opening. Oh, I need to can I copy link? Yeah, I can copy the link. Right, let's see here. So we're gonna as the confusion matrix, right? Con So we're gonna run the no, I'm gonna run everything till here and before. Yeah, run anyways. Uh I can't have two sessions at once. Hmm. I need to just memorize the logits and stuff that I have. So my logit looks like this. I also print out the y logit shape. I should do it. 3210 is the shape. That's what it looks like, 3210. And now we're gonna terminate other sessions and yep. And yeah, run before. How did I run before? There we go. Yeah, that's fine. That's fine. I don't think that should change things much. And let that load. It is it running or I guess it's oh, okay, okay, it's running. It's running, yeah. So let it reach. Where's the part where he prints out the rather plots the predictions? I think it's here, isn't it? Let me just check if I have my mic. Yeah, I have my mic and desktop audio open, so they're not mute. They're not on mute, so it should be okay. It is taking some time, but yeah, it is what it is. So where is it actually stuck on right now? Is it stuck or no? It looks like I am. Uh, Did it run? Nah, it's running this. Yep. So let's yeah, I think we can just do this manually now. You could have deleted the other code block too, but let's just do this because the trading might take time again. Oops. Yep. Gotcha. Setting up the loss function, and this is the training part. Right, we seem to be getting good accuracy. Our loss, I think our loss was lower when I ran it. Anyway, okay, let's why do I have this big blob of thing going on here? And moment of truth. Okay, that works fabulously well. Now we could just go with this uh collab not bug, but I wanna make my life difficult, so we'll try to debug debug or figure out. Anyways, alright, let's see what's going on here now. Is the question everyone wants answered. Right. Print y logit and its shape. And here we go. Wait, what? Well, that is 30 to 10. Okay, this is difficult now. Um, hmm. Can we copy the code that we wrote? So somewhere before this is where we need to change. I mean, this code and that code is exactly the same, so something way before this is where our code is erring out apparently. Something to do here too because hmm, let's see. Just to make sure that the problem is not with this part. To now cancel it. Never mind. Hmm. What can it be then? Why is it working here but as it's not working there? Like that would, I mean, it shows that something's wrong with our card, but you that already in me. Okay, run it. Yeah, manage session. Oh geez, I'll have to run everything again. I don't wanna do that. Uh, what was the shape again? It's not anything to do with this. Not anything to do with this or this. Probably something to do with this part, but we literally copy pasted this part and it seems to work on the other side. So could it be something to do with the model? Hmm. Yep. I don't want to do it, but let me change the run. Nah. You know what? Terminate the other session. Oh, jeez. But at the to our mark on stream already, and we are yet here trying to figure this out. Done before. I'm gonna put on the fan here. It's getting way too hot. We'll disturb the stream a bit. I'll turn it off if anyone joins. Oh geez, I can hear the ad through my headphones itself. I need to get something which wouldn't disturb the stream and yet I can remain cool, you know. Anyhow. If this doesn't work, I'm gonna just overlook it and continue with the tutorial anyways. I mean, I'm pretty sure we can figure out the problem here, but I don't wanna waste this much time. It already works on the other notebook anyhow. Okay, run. Okay, what's happening here? Of course. Oh, that's my microphone here. Can you guys hear this snap? Oh, you can. Huh. I think it's because of the fan, like my area voice area got expanded or something. You changed the code, right, to create the model? Wait, okay, let me turn off the fan. I have a feeling, well, that this might work, but nah, that didn't work. Maybe it did work. Which code am I running? Guys, change anything here? I want the exact same code here. Uh, we're gonna get to that code fast by logic. Hmm. For some reason, this did end up working. Our model is working, but something in the second block is. Okay. Have the. Let me see. Let me see. Oh wait. Wait, what? Huh? Why isn't this working now? It doesn't look like 89 whatever percentage accuracy to me. Maybe we copied something wrong in the training loop, perhaps. It says our model is 89% accurate. Mm, let's do another sample. Let's. What is going on here? Okay, okay. You know what? Right, okay, okay. We can solve this. We can solve this. Come on. We'll definitely solve this. Okay. Let's see here. Let's see here. Even if it means we copy paste each individual cell, we are gonna solve this. So hmm. Hold on a second, hold on a second. What would be the easiest way to debug this is the thought that's going on in my mind. For some reason, our accuracy says 89%, yet the model is unable to make correct predictions. What that tells me is somehow, somewhere, we're messing up with the conversion to label part. So eval model says that the model accuracy is 89%. Alright, okay. Let's see what eval model does. So, eval model actually doesn't. Wait, what? Expect all tensors to be on the same device. Let's see. Yeah. I don't think you just does a lot should I remove? Nah, I don't think I need to remove that. Now let's see where else we are. Oh, do we have? I thought we had two definitions of val model. So let's go to the part where we are evaluating this model here. And what type? Weight is a dense tensor. Let's 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 copy this for eval model. Okay. All right. Let's see what this is about now. Model is on GPU, but your data is on the CPU. Hmm. Send everything onto. Can we do x.gpu for test data loader. See here. To device and moment of truth, we can't. Has no attribute. Okay, I don't think we need to do this, which means the problem is with our model too. But we are sending it to our device. Okay, let's do one thing. Eval model. Maybe it's because X and Y needs to be sent to the device. X comma Y is equal to X dot to device. Y dot to device. Okay, let's see. And that worked. Okay. We got 89% accuracy. Alright. How does what actually happens here? So, for X comma Y in data loader, hmm, it's pointless, but still, let's just put that in there. Okay, so coming back to this now. I would make predictions. For sample and data, we do prediction probabilities. And how are we creating this prediction probabilities? We take a sample size 9, we pass it test data, so we get our test samples and test labels. Okay. That's correct. Uh-huh. Rate the sample size. Wait. Okay, hold on a second. What's that prediction? How exactly are we getting the prediction label? We make use of the make predictions part. So our prediction probabilities. Yeah, we need the prediction classes for this to make sense. 37245. That's 100% accuracy, right? So if we plot it, beginner's luck, maybe. Now it's working. Let's wait another. And not exactly correct, but not bad either. So this is 100% accuracy. Hmm. So it's doing good now. So was it to do with the was it to do with the two device? Hmm. Alright, okay. Here's what we're gonna do. That works, then hopefully. Nah, that didn't work. That did not work. But now this part is working for some reason. It's still pretty good. That's still pretty good. Okay. So now the problem is just with this part of the code. Hmm. That's a pullover, all right. We need to. That is a trouser. Yeah, that's a trouser. Does the prediction say though? But for the says an angle put, an angle put. What does this tell me? Wait, okay, okay. Go back, go back. It says data.target is not the same as test data loader. Huh? What is test data? Oh, wait a second. We finally solved it. The issue was that I shuffled the data while what's it? Mm, Daniel did not shuffle the data. So I was comparing against the wrong targets. My model was giving us the right output, but since I was comparing it to a false output because I shuffled the data, uh, there was no use in us matching the results. Oh no. We finally solved it, and okay, now what? Not if no module name torch metrics. Okay, solved. Let's resolve that. Now what? List object has no attribute and I think I can just walk through this now. But I believe that was the main issue. And I'll just check. One second. I'll be back. All right, and I am back. So yeah. Where were we? Yeah. What's the issue with this? The phrases have one on. Hmm. There we go. That would probably be why. We don't need to print. Okay, let's just stop that. Stop. Right. And remove that. Run that. And then we go in here. Now what? Now what's the issue? The subject has no attribute and is it a tensor? Okay, why is that not a tensor? Hmm. If predictions have one dimension more than target, predictions should be a float tensor. Oh, this has one more tensor more than the target tensor. Of course. We finally did it. This is why you should always follow the tutorial as it is. I don't know why did I shuffle that to true, or maybe it was already shuffled. Anyway, we resolved it. It took us quite some time, but I guess it is it reveals what you do on a daily basis as a developer, doesn't it? It's always the most silliest things which come out to be the which come out to make most problems. Anyway, I'm happy that we finally resolved it. We didn't make much progress today, but let's just finish. How long is this? Let's just finish this part of it.
Darkened, with all of the values and no values here, no values here. Because that means that the predicted label lines up with the true label. So in our case, we have definitely a very dark diagonal here. But let's dive into some of the highest numbers here. It looks like our model is predicting shirt, when the true label is actually t-shirt.
Our model is predicting shirt when the true label is actually a t-shirt.
/top. So that is reflective of what we saw before. Do we still have that image there? Okay, we don't have an image there. But in a previous video, we saw that when we plotted our predictions, the model predicted t-shirt/top when it was actually a shirt. And of course, vice versa. So what's another one here? Looks like our model is predicting shirt when it's actually
a coat. And it's predicting a t-shirt when it's actually a shirt.
a coat. And now, this is something that you can use to visually inspect your data to see if the errors that your model is making make sense from a visual perspective. So it's getting confused by predicting pullover when the actual label is coat, predicting pullover when the actual label is shirt. So a lot of these things, clothing-wise and data-wise, may in fact look quite the same. Here's a relatively large one as well. It's predicting sneaker when it should be an ankle boot. So it's confusing two different types of shoes there. So this is just a way to further evaluate your model and start to go, maybe our labels are a little bit confusing. Could we expand them a little bit more? So keep that in mind. A confusion matrix is one of the most powerful ways to visualize your classification model predictions. And a really, really, really helpful way of creating one is to use Torch Metrics Confusion Matrix. And to plot it, you can use Plot Confusion Matrix from MLXtend. However, if you're using Google Colab for these, you may need to import them or install them. So that's a confusion matrix. If you'd like more classification metrics, you've got them here. And you've got, of course, more in Torch Metrics. So give that a look. I think in the next video, we've done a fair bit of evaluation. Where are we up to in our workflow? I believe it's time we saved and loaded our best trained model. So let's give that a go. I'll see you in the next video. In the last video, we created a beautiful confusion matrix with the power of Torch Metrics and MLXtend. But now it's time to save and load our best model, because if we evaluated it, our convolutional neural network, and go, you know what, this model's pretty good. Let's export it to a file so we can use it somewhere else. Let's see how we do that. And by the way, if we go into our keynote, we've got evaluate model, Torch Metrics. We've been through this a fair few times now. We've improved through experimentation. We haven't used TensorBoard yet, but that'll be in a later video. And save and reload your trained model. So here's where we're up to. If we've gone through all these steps enough times and we're like, you know what, let's save our model so we can use it elsewhere, and we can reload it in to make sure that it's saved correctly. Let's go through this step. We want number 11. We're going to go save and load best performing model. You may have already done this before, so if you've been through the other parts of the course, you definitely have. So if you want to give that a go, pause the video now and try it out yourself. I believe we did it in notebook number 1. We have, here we go, saving and loading a Pytorch model. You can go through this section of...
We'll just use our Word docs to do that real quick. Alright, that's it then, huh? We just do model 2 and state dict, and try to create the path, don't we? Creating a path in Python. So. Hmm. Before we do this though, let us create the path. models from OS import make dir and it's mkdir, not yeah, makes sense. Mkdir dir access okay access or access okay, something like that, right? Make dir in Python. Okay, maybe it's make dirs. Okay. Yeah, access okay is true. Let's see if this works. I'll just import os dot make the irs and access okay. Oh okay, oh it's access okay, not access okay. Okay, how do I, is it this button over here? Yeah, there we go. But now we save that to directory slash CNN, I mean fashion model dot pt, and that should do it hopefully. And there we go.
Section number 1 on your own and see if you can do it. Otherwise, let's code it out together. So I'm going to start with importing path from pathlib because I like to create a model directory path. So create model directory called models if they don't exist, and exist okay also equals true. So if we try to create it but it's already existing, we're not going to get an error. That's fine. And next, we're going to create a model save path. Just going to add some code cells here so we have more space. O3 Pytorch. So now if we got PTH, and if we this is a good way to start setting the model state dict path, and we can save a model by calling torch, so model 2 biases and all that sort of jazz. Beautiful. So when we first created model 2, and we can leverage these later on, as you've seen before, to make predictions. So I'm not going to go through all those, but that's what we're saving. And 3. And now let's have a look in here. Do we see what happens when we load it in? So create a new instance. Because we only saved the state dict of model 2, we need to create a new instance of our model 2, or how it was created, which was with our class fashion mnest v2. If we save the whole model, we could just import it to a new variable, but I'll let you read back more on that and the different ways of saving a model in here. There's also a link to the Pytorch documentation. Would highly recommend that. But let's see it in action. We need to create a new instance of our fashion mnest model v2, which is our convolutional neural network. So I'm going to set the manual seed. That way when we create a new instance, it's instantiated with the same random numbers. So I'm going to set up loaded model 2 equals fashion mnest v2. And it's important here that we set it up with the same parameters as our original saved model. So fashion mnest v2. Oh, we've got a typo here. Oh, fashion mnest model v2. Wonderful. So the input shape is going to be 1 because that is the number of color channels in our images. Test image.shape. Do we still have a test image? Should be, oh, well, we created a different one, but our image size, our image shape is 12828. Image shape for color channels, height, width. Then we create it with hidden units. We use 10 for hidden units, so we can just set that here. This is important. They just have to, otherwise, if the shapes aren't the same, what are we going to get? We're going to get a shape mismatch error. And our output shape is what? Is also going to be 10 or length of class names. If you have the class names variable instantiated, that is. So we're going to load in the saved state dict, the one that we just saved. So we can go loaded model 2 dot load state dict, and we can pass in torch.load in here. And the file that we want to load, or the file path, is model save path up here. This is why I like to just save my path variables to a variable so that I can just use them later on instead of retyping out this all the time, which is definitely prone to error.
Let's make this a new variable. File name and replace this part with file name, and here we'll have file name.
Errors. So we're going to send the model to the target device. Loaded model 2 dot to device. Beautiful. Let's see what happens here. Wonderful. So let's now evaluate the loaded model. So evaluate loaded model. The results should be very much the same as our model 2 results. So model 2 results. So this is what we're looking for. We want to make sure that our saved model saved these results pretty closely. Now I say pretty closely because you might find some discrepancies in these lower decimals here, just because of the way files get saved and something gets lost, etc., etc. So that's just to do with precision in computing. But as long as like the first few numbers are quite similar, well, then we're all gravy. So let's go torch, manual seed. Remember, evaluating a model is almost as, well, it's just as important as training a model. So this is what we're doing. We're making sure our model saved correctly. Before we deployed it, if we deployed it and it didn't save correctly, well, then we would get less than ideal results, wouldn't we? So model equals loaded model 2. We're going to use our same eval model function, by the way. And of course, we're going to evaluate it on the same test data set that we've been using, test data loader. And we're going to create a loss function, or just put in our loss function that we've created before. And our accuracy function is the accuracy function we've been using throughout this notebook. So now let's check out loaded model 2 results. They should be quite similar to this one. We're going to make some predictions. And then if we go down, do we have the same numbers? Yes, we do. So we have 56829, 56829, wonderful. And 31358, 31358, beautiful. It looks like...
Wait, let me see if I have the same result. I should have it. And there we... Oh wait, it was so... But, show me the result so I can come back. Okay, made a typo there. Looks about right.
our loaded model is the same result as our previously trained model before we even saved it. And if you wanted to check if they were close, you can also use torch.isClose. Check if model results, if you wanted to check if they were close programmatically, that is, because we just looked at these visually. Check if model results are close to each other. Now we can go torch is close. We're going to pass in torch.tensor. We have to turn these values into a tensor. We're going to go model to results. And we'll compare the model loss. How about we do that? We want to make sure the loss values are the same. Or very close, that is, with torch.isClose. Torch.tensor. Model, or we want this one to be loaded model 2 results. Model loss. Another bracket on the end there, and we'll see how close they are. True. Wonderful. Now, if this doesn't return true, you can also adjust the tolerance levels in.
It should be is close without the underscore. Yeah, there we go.
So we go atol equals, this is going to be the absolute tolerance. So if we do 1 to the -8, it's saying like, hey, we need to make sure our results are basically the same up to 8 decimal points. That's probably quite low. I would say just make sure they're at least within 2. But if you're getting discrepancies here between your saved model and your loaded model, or sorry, this model here, the original one, and your loaded model, if they're quite large, so they're like more than a few decimal points off in this column or even here, I'd go back through your code and make sure that your model is saving correctly. Make sure you've got random seeds set up. But if they're pretty close, like in terms of within 3 or 2 decimal places of each other, well then I'd say that's close enough. But you can also adjust the tolerance level here to check if your model results are close enough programmatically. Wow, we have covered a fair bit here. We've gone through this entire workflow for a computer vision problem. Let's in the next video. I think that's enough code for this section, section 3, Pytorch computer vision. I've got some exercises and some extra curriculum lined up for you. So let's have a look at those in the next video. I'll see you there. My goodness.
I think we'll continue in the next stream. We spent a majority of the stream debugging the confusion matrix issue, which is it's a bummer that we couldn't make much progress today. But I would argue that debugging is a part of the job, and sometimes this is reality. Sometimes it takes up this much time, and it's always for the silliest reasons. Most of the times, anyways. We have officially hit our goal, our follower goal, as of today. And yeah, I'm happy for that. And yeah, let's I'll see you all in the next stream. This is me, Shazan AI, signing off. Take care.